So next is compound sections. Compound sections formed by strengthening a rolled section by welding a cover plates on top. So you weld a cover plate on top, you have a compound section. Basically, you want to strengthen the rolled section, such as the equal angle, for example, or an I-beam. So you want to strengthen the top part. So you add a plate on the top and you welded the plate to the universal beam. So you have a strengthened roll section. So combining two separate roll sections, example crane girder, the two members carry loads from separate directions. So you combine two separate roll sections, so you can carry loads from separate directions. So connecting two members together to form a strong combined member, example laced and batten members. So these three types of compound sections, of either you adding a plate on top of a rolled section, or you combine two rolled sections, or you're connecting two members together to form a strong combined member, is the definition for compound section. So this is an example of a compound section. We have strengthening of I-beam, a universal beam using plate, which is compound beam. You have combining two separate roll section. You combine a C channel. You combine channel with the universal beam. You have a crane girder. Then you have a crane girder, or you combine a batten member. So you combine a plate of two beam here. So you can have a larger cross section of beam, or a laced member. You combine a column with lacing here. You basically connect the two members together so that you have a bigger member. And next one is a build-up section. Build-up sections are made by welding plates together to I, H, or box members to produce a plate girders, build-up column girders, or column respectively. So I have a girders here, a build-up column, box girder, or box column. So basically, you combine a plate rather than you hot rolled it into a universal column. You combine the three plates here to produce a build-up column, or four plates here to produce box girder. So basically, that's a build-up section. You are not hot roll. You don't hot roll it into a section, but rather you weld it into a section, a required section. And next is a cold roll section. Thin steel plates can be formed into a wide range of sections by cold rolling. So not hot rolling, you cold rolling it. So most important uses of cold rolled sections are for purlins and sheeting mills. Purlins are basically for staging for your sometimes steel structure. For slab, they use a purlins there before applying a slab deck. So you have macam rumah kayu, they have a purlins. And basically, we don't often see this, but if you have experience in steel structure, steel framing, so purlins is important as sheeting rails. And also purlins is used for roofing. For roofing, they have purlins before they put clay tiles on top of the purlins. So three common sections in cold roll sections are Z, which is basically a letter Z. Sigma is a symbol of sigma, and lip channel. So this is example of Z section. So basically, you can see there Z sigma section. Often see this metal product. So roughly, you can say that it is for a beam or lip channel. You have like a channel, but you have a lip at the end of the channel. So to recap, you have cold rolled section where you roll the sections. You roll the thin plates in cold temperature to form into Z, sigma, or lip channel. So basically, you bend the steel plate into your required section. Cold rolled sections. Build up section, you weld the plates into sections that you required. Either it's a build up, box girder. And then also compound section, you combine the section, rolled section. You combine the rolled section, you strengthen it, or you combine, or you lace together to produce a bigger, stronger sections. And also rolled and formed sections. You roll the sections in a high temperature, hot sections being rolled to produce your rolled section. You have 6 types of section. So these are your 4 steel sections being used as a finished product. So the next one we're going to explain, which is a common one, is the reinforcing steel. Reinforcing steels, which is often called rebars, which is a short term for reinforcing bars. Reinforcing steels are placed in concrete members to improve the tensile strength of concrete. As we know, concrete is brittle, not very strong in tensile strength, basically 2 megapascal, 2 Newton per millimeter square. So reinforcing bars or rebars or reinforcing steels being added to the concrete to produce a reinforced concrete. So bars have surface projections. You have rib bars. You can see a protruding surface of steel bars. I can show you in the example here. Not very clear here. You have a surface projection, basically a ribbed bar. You have a rib on the bar surface that provides better bond to concrete. So increase the friction between the concrete and reinforcing bar, so that during flexural, during bending, or during tensile, the bar won't be slipped out of the concrete. So the characteristic strength of reinforcing, the first one is hot rolled mild steel, all sizes. The basic strength is 250 Newton per millimeter cube, and for high yield steel is 460. So before this, people would put T at the front or R at the front to differentiate between hot rolled mild steel or high yield mild steel. So basically high yield is stronger than hot rolled mild steel. So in this photo is reinforcing bars and welded wire fabric provides tensile strength for concrete members. So this is commonly seen on construction site. You have reinforcing bars here, large diameter, usually the smallest being 6 mm. The largest I've seen before is 40, but you can ask the factory to produce up to whatever size you want. But basically, the larger you have, and the larger diameter you have, let's say for 40, the problem is with handling it to form it. Larger steel, so for example at 40 mm diameter, one piece of that 12 meter length of 40 mm diameter reinforcing bars is heavy. So the workers may require crane assistance to arrange the bars into formwork before being cast. So using smaller diameter of concrete may reduce the cost of renting a crane, but may require larger number of steel being placed in the concrete. But using using larger diameter of reinforcing bar will reduce the number of steel bars in the concrete, which in turn avoid congestion in concrete and will prevent any segregation or any honeycomb in concrete, which is very bad towards the concrete integrity. So it's a pro and cons, depends on the requirements. I've seen 40 for larger columns to carry a larger load. So but for housing areas or building of double story, there is lesser chance to encounter such problems, because they use smaller steel due to smaller load being applied. At the bottom of the figure here shows the BRC. We often call it BRC, but the term is welded wire fabric, which is often used for slab, because it is easier because you have because you have a large prefabricated arrangement, so you can just lay the BRC there. So based on the design, so just lay, so you don't need to tie each and every strand of these reinforcing bars. So you save up the duration, and also requires less worker and less material to tie up to produce. As opposed to this is a larger, because in Malaysia they don't have BRC so large, as opposed as in my previous project here. They use larger steel, the larger reinforcing bars. So factory don't produce this size of BRC, so we need to tie up. So as you can see there, each and every intersection of steels being tied up, almost all of it. So this work here requires a lot of manpower and a lot of wire, a lot of kilograms of wire to tie up the amount duration as opposed to the BRC. So BRC saves up time, saves up material, but depends on the factory that produces it. So as you can see, need to arrange the bar according to the spacing, and then you have to have the amount of worker here. This is the amount of worker. One group here just to arrange the steel bars, and one group here just to tie up the bar. So the amount, the duration they need to produce. This is to produce a deck slab. This is the slab of the bridge. This one is a project at the Selangor, Sepang. The bridge is to cross the Sungai Sepang Kecil, but the name does not justify the size of the bridge, the size of a river, because we have another river at the other side of town, which is Sungai Sepang Besar. So Sungai Sepang Besar is narrower compared to this Sungai Sepang Kecil. So we have a 3 span of bridge, a 20, 30, 20. So our total length of bridge is 70 meter. So you can see here, this is a dowel bar. So dowel bar here, where you're going to cast the approaching slab. They call it approaching slab. So you have approaching slab here. This is your deck, bridge deck being like a hook to your plinth of the plinth of the abutment. So this is steel, as you can see here, a projection, or we call it rib. We have a projection of steel to increase the friction between steel, reinforcing steel and concrete. So this bar is for the wing wall of the bridge. So wing wall, and then to the parapet of the bridge. So basically serves as the guard